Now to get the transfer function, okay, so let's get the system transfer function. Okay, so to get the system transfer function, okay, obviously what should we do? Like take Laplace transform on both sides and apply 0 initial conditions, right? So this is a very important step, and since we have done this step many times, like I am just going to skip and go directly to the final answer, but I suggested you do it completely, right? So as I keep on telling you, like you should always write the Laplace transform completely, so let me do it once more. So please note that the Laplace transform of the second derivative of theta 2 is going to be s squared theta 2s minus s times theta 2 0 minus theta 2 dot 0. Okay, of course it's obvious from the context that the second two terms are initial conditions, okay, where theta 2 is evaluated in the time domain, right? So and the Laplace transform of theta 2 dot is going to be equal to s times theta 2s minus theta 2 0. Okay, so we need to keep in mind all those things, right? So once we essentially apply the Laplace transform and substitute initial conditions to be 0 and collect the terms and so on, what are we going to get? We are going to get the following, okay, theta 2s is going to be n2 divided by n1, the whole thing divided by j1 n2 by n1 whole square plus j2 times s squared plus f1 n2 by n1 whole square plus f2 times s. Okay, this multiplying Tm of s, right? Correct? That is what the first term is, right? Okay, on the right hand side. Then what we have, we have another term, right, the load torque minus 1 divided by the same denominator, okay, j1 n2 by n1 whole square plus j2 s square plus f1 n2 by n1 whole square plus f2 s, okay, the whole thing multiplying TL of s. Okay, so this is what we will get, all right. Is this correct? Did I miss out something? I think it's fine, right? Okay, so you see that finally the output of the system theta 2 has two components, right? So this component is the one due to the input. So the first term is the one due to the input, okay. The second term is due to the load torque, right. So please note that, like if I want to move the output shaft to any position, right, you can immediately see that the load torque is going to play a role, right. So as far as the output responses, the response of the system is concerned, right. So we need to keep that in mind. So let's say you give a step voltage as step input torque for Tm, the final theta 2 is going to be dependent on the load torque, right, obviously, okay. But the plant transfer function per se is the function multiplying Tm of s, right? That is the plant transfer function, right? Because the one relating the input and the output. Okay. So, just for what to say for further analysis, okay, and design, momentarily we will neglect the load torque, okay, so that like we can carry on with the analysis. Then we will revisit towards the end and see how our design is affected by the load torque. Okay, that's something we'll come back and look at it. Okay, so for the time being, let's neglect the load torque TL. Okay, this implies that the plant transfer function P of s, which is going to be equal to theta 2 of s divided by Tm of s. This is going to be equal to N2 by N1 divided by J1 N2 by N1 whole square plus J2 S square plus F1 N2 by N1 whole square plus F2 times S. Okay. This I can rewrite it as A divided by, just for the sake of notational simplicity, right. So, if I have to write all the parameters in the general form again and again, right, that is going to be very cumbersome. Okay. So, let's write it as A divided by some S squared plus BS, right. So, obviously, you know, like what are A and B? So, here what I am doing is I am just saying that the parameter A is going to be N2 by N1 divided by J1 N2 by N1 whole square plus J2, right. That is what I am essentially taking A as, and B is essentially F1 N2 by N1 whole square plus F2 divided by J1 N2 by N1 whole square plus J2. Okay, so that is what we are considering, right. So, immediately we can see that this is a second order system whose transfer function is of the form A divided by S times S plus B. Obviously, A and B are positive, right. One can immediately note that the parameters A and B are positive. Okay. And what are the system or plant poles? We have a pole at the origin, we have a pole at minus B, right. So, is this plant going to be stable? No, right. So, because of course, it depends on how we look at it. As we discussed, some people call it as critically or marginally stable, but we know that when we have a non-repeating pole at the origin, you give a step input, the output will become unbounded, right. So, you can immediately picturize it. Let us say you have a motor shaft and a gear transmission, you give a step voltage, you will see the output shaft will keep on rotating. You might have observed it even in your experiment on DC motor that you some of you might have done, right. So, essentially the output shaft might have just kept on rotating, right. So, if you do not apply any control to the system, right. So, that is what is going to happen here. Okay. So, now the question is, what do we do, right. So, for essentially once again the sake of simplicity, you know, like let us take, so that we work with some numbers rather than parameters. Let us say we take A to be 2, B to be 10. Okay. So, this implies that the plant transfer function is, let us say, 2 divided by S times S plus 10. Okay. So, that is what I am just considering some number, right. So, essentially, so that like we work with some numbers, right. So, now the question is for us to design a closed loop feedback system, and then you know, like ensure that the closed loop system is stable, and then ensure that it satisfies some performance requirements. Okay. So, that is the second task which I am going to pose. Okay. So, task 2, so I hope I call the first one as task 1. yeah, task 1, right. So, task 2, oops, yeah, task 2 is a design a stable unity negative feedback control system that satisfies the following, okay, settling time, less than, let us say 2 seconds, peak overshoot MP less than, let us say 10%. Okay. So, the task for us is to design not only a stable closed loop feedback system, but also one that will stabilize, that will satisfy these performance requirements, right, of settling time less than 2 seconds and peak overshoot less than 10%. Okay. So, what I am going to do is that, like, I am going to stop here. Okay. So, I will let you think about it, and then, like, we will complete this task tomorrow. Okay. So that we go through the entire control design process once, right. As I told you, we are at the halfway mark before going into the next chunk of topics. Now, I thought, let us work out a problem from start to finish, right, based on whatever we have learned, so that we understand what. So, just try out a proportional control, like, you will see that in this case, even a proportional controller would stabilize the closed loop system. Okay. And then think about how you would you can use root locus to ensure that you can satisfy these performance requirements. Okay. Please think about that, and then, like, we would continue in the next class.